biggest shift this week is that robotics is moving from asking whether a model can see motion to whether that motion can actually survive contact with the real world. One result shows that polished video quality is a terrible proxy for executability, while another proves you can slash real robot data collection by leaning on simulation and still transfer zero shot. And the third pushes adaptation even further, generating task-specific policy weights from a prompt and a demo video alone. Keep watching, because the interesting part is what these systems say about the next generation of robot generalization. Let's explore the first paper, Dream.exe. Can video generation models dream executable robot manipulation? Dream.exe, from Show Lab at the National University of Singapore. With the evaluated frontier systems, including Google DeepMind's VO 3.1, NVIDIA's Cosmos Policy, Minimax's Hailuo 2.3, Kuaishou's Kling 3, ByteDance's Seedance 2, and Alibaba's Wan 2.7, asks a direct robotics question. Can the motion in a generated video be executed as a real manipulation policy? The paper builds a video-to-execution benchmark over 101 manually curated RoboCasa 365 tasks spanning 3 difficulty levels, then converts each generated clip into a 7D robot trajectory using co-tracker point tracks, DVD LoRa depth estimation, cache-based rotation recovery, and gripper event inference, before replaying it in MuJoCo, RoboSuite on a Franca Panda. Across 8 models, the key result is that visual quality is a poor proxy for physical executability. Physical plausibility is essentially uncorrelated with binary task success, with Pearson R equals -0.03, and VO 3.1 can rank highest on task adherence while achieving only 3.3% level 1 success. By contrast, general-purpose generators such as Seedance 2 and Wan 2.7 reach 15.1% and 21.4% task success at level 1 and level 2, while the robot-specific Cosmos Policy Benchcam peaks at 20.8% level 1 Steradium B, but does not dominate task success. The strongest trajectory following result comes from Cosmos Policy Benchcam at 0.77 EEF Visual HSD and 0.833 DYN, yet the study shows that better geometric fidelity does not guarantee task completion. The paper's main contribution is therefore a new grounding test for video world models. Not whether a manipulation video looks realistic, but whether its implied motion can actually make a robot succeed. Let's explore the second paper, Oasis from Simulation Data Collection to Real-World Humanoid Loco Manipulation. Oasis, from China Telecom's Tele AI and collaborators at Fudan University, East China University of Science and Technology, and Shanghai Jiaotong University, is a simulation-first pipeline for humanoid loco manipulation that replaces real robot teleoperation with scalable simulation data. It reconstructs physics-ready objects from single-view real images using Hunyuan 3D and Qwen 3 VL, then lets operators teleoperate a simulated Unitree G1 through Pico 4 Ultra VR, recording only state sequences for later offline photorealistic replay with texture, lighting, and camera extrinsics randomization. The policy stack uses a hierarchical design, a flow-matching high-level planner conditioned on frozen clip text features, Dynov 2 multi-view images, and 2 frame proprioceptive history predicts 2 frame reference motion chunks, which a low-level controller converts into 3 whole body joint angles. In real robot deployment, Oasis cuts data collection time to 15.2, 19.1, 25.2, and 28.4 minutes for 50 successful trajectories across 4 tasks, versus 17.lime, 26.8, 40.2, and 44.8 minutes for real teleoperation, reaching up to 1.84 times speedup. Zero-shot transfer is especially sensitive to visual augmentation. Removing all randomization drops average success to 0.05, while the full pipeline reaches 0.83 after rendering each trajectory in 20 randomized environments. On the Unitree G1, simulation-only training matches or exceeds real data training on tasks such as place cup and box, lift basket and place cup, wipe monitor, and kneel and wipe under table, showing that high-fidelity simulation can substitute for expensive real-world collection and improve robustness through broader visual coverage. Let's explore the third paper, Robotic Policy Adaptation via Weight Space Meta Learning. Robotic policy adaptation via weight-space meta-learning introduces Wizard, a weight-space meta-learning framework for vision, language, action robotics that generates task-specific LoRa adapters from a language instruction and a short demonstration video in a single forward pass without action labels, test time optimization, or privileged goal images. Built around the Frozen Pi 0.5 policy, Wiser meta-trains on expert LoRa updates paired with multimodal task embeddings and adds 2 robotic-specific design choices: explicit per-layer scale prediction and cosine alignment in weight space. On the Libero benchmark, the method lifts zero-shot success on the held-out Libero spatial suite from 0.19 for the MTVLA baseline to 0.4, while also improving Libero goal from 0.14 to 0.22 and Libero object from 0.01 to 0.03. The paper reports up to about 2 times gains on unseen dataset collections and up to about 14 times on unseen tasks. On a real Franca Emica Panda with 3 Intel RealSense cameras, Wizard improves average success from 0.22 to 0.41 across 5 manipulation tasks after the same real domain grounding, and its generated adapters can also warm start fine-tuning to reach 96% expert success in 70 steps instead of 90. The ablation study shows that pure MSE reconstruction fails completely, scale-aware supervision raises average success to 0.27, and adding cosine alignment further increases it to 0.33, underscoring that stable parameter scale is essential for robotic weight generation. That's a wrap on today's AI paper highlights. Thanks for watching.